In this video, we'll be studying volumes of revolution by the method called shells. This is a second way to compute a volume of revolution as opposed to the disk washer method that we saw in the previous two videos. This method relies on what's called a shell instead of a disk or washer. In other words, it's not relying on a right circular cylinder shape. Let's see what we mean by a shell. A shell takes the strip, or the thin rectangle that it is drawn, and rotates it parallel to the axis of revolution, or the axis of rotation. In this way, it is creating, instead of a disk or a washer, a shell, which is like a hollow circular cylinder where the wall has thickness of the differential dx. If we rotate around the other axis, the differential, of course, would be dy. Let's take a look now at this particular example and some graphs that were drawn using Calc 3D. Here is the region bounded by the function f of x equal x squared, the x-axis, and the vertical line x equal 4 revolved about the y-axis. As you can see right here in the picture on the far left, we have the curve y equal x squared in quadrant 1 only. The x-axis is here, the vertical line x equal 4 is represented on the far right, and of course this gives us a closed region in here in this shape. You can see right here one thin strip or one thin rectangle. Because the narrow end or the short end of the rectangle is horizontal, that makes the differential dx. You can also see that the radius is going from the y-axis out to the strip. When we start to rotate, notice that this is sort of like a stick of gum that's being bent around into a circle. In other words, you're taking the stick of gum and rotating it until it forms a circle. When you're done, you get something that looks like this. We do this for each thin strip or each thin rectangle, which will give us a stack of them, one inside the other. This method, in reality, has an outer radius on the shell slightly longer than the radius on the inner side, and hence the back edge of the plate would be just a little bit longer than the front edge of the plate. We want to know what the volume of an individual shell is. Before we discover that, however, let's take a moment to switch to the webcam and show you in the real world what a shell would look like. Recall that what we're taking is sort of like a long piece of gum, and we're bending the piece of gum into a circle. Now, if I take this piece, notice that this piece does have some thickness to it, and it does have length, and it does have width, and I'm bending it into a circle. What happens is I'm taking one shape, for example, this shape right here, and I've got it bent into a circle. So first it looked like this, sort of like a piece of gum with different thicknesses on each side, and I'm rotating it into a circle. Then I'm going to take another shape and fit it around it, so that when I'm done, I'm imitating the shape of my graph with the heights of each of these shells. Each little stick of gum turned into a circle is called a shell. So I can take my next piece of gum and wrap it around so that it creates another shell on the outside. Now mine should be meeting in the back, but I've kind of run out of space. That's what it looks like when you get it all together. And you're approximating the volume of this solid with the heights of each shell representing the height on the graph. Let's take a look at another way of thinking about the shells. If you take a set of toddler stacking cups, and by stacking cups, I basically mean one of the toys where you stack a cup inside of another cup. If you take each one of these, they are, of course, tubes, right? So they're basically circles. They do have a little bit of thickness to them, but not much. But it's like a stick of gum. And then when I put them together, I can approximate the shape of the curve by the height of each shell, where each shell is formed by a different stacking cup that I have here. I take the volume of each individual shell and add them together to get the volume of the whole thing. Notice that it is when I put all the stacking cups together that I get a solid, and I would need more stacking cups on the inside until it disappeared into a single spot. Now, what would the volume of one of these be? Let's take a look at the bigger piece so that we can actually think about it with a slightly larger example. This, of course, when rolled out, a piece of gum more or less looks like a rectangle. That means that we have a length and we have a width. However, as a piece of gum, or in this case, an air filter, I do also have some thickness. So I'm going to be taking the length times the width times the thickness to get the volume of this piece. This shell, when rotated together, becomes a circular shell, but notice that all of our shells are hollow on the inside. It's not like the disc that was solid, and it's not like the washer where we had an annulus. This instead is an actual tube, and we're using a lot of tubes to create our solid. The volume of this is the length times the width times the thickness. The thickness is going to be given by the differential. Let's go back to our notes and see how we can calculate the volume of this piece. By cutting open that circular tube and making it into a shape like a piece of gum by flattening it out, we can approximate the shell with this thin box area or this piece of gum area. Note that the piece of gum has length and it has width, but it also has a little bit of depth. This depth will become the differential, either dx or dy, depending upon which axis of rotation we have. Because we're using the shell method, we are going to draw our strips so that they are parallel to the axis of rotation, which here in the picture is the y-axis. That makes our thin strips or our thin rectangles be vertical as well. Think shell, double L, parallel. Once we flatten out the shell, we can see that the length of it actually corresponds to the rolled up tube. In other words, the circumference of the rolled up tube is the length of it when we open it like a piece of gum. That means it's 2 pi r. What is the radius? The radius extends from the y-axis to somewhere on the curve of f of x. But the distance from the y-axis out is just the x-coordinate. Therefore, our length becomes 2 pi x somewhere on that curve. What is the width of the piece of gum? The width of the piece of gum is the height of the curve. That would be the y value on the function f of x. The y value on the function becomes the length of the strip. So the height of the strip is the width of the piece of gum. That's the function value f of x, and that gives us the y value. Then the derivative, or rather not derivative, but the differential is given by the depth. The volume of the piece of gum as a box is length times width times height. The length is 2 pi r, which is 2 pi x. The height is the y value, which can be written f of x, and the height of the piece of gum or the box is the depth of it, which can be written with the differential dx. Let's now use this to compute the volume of the entire solid by adding the volume of each individual shell together. That sounds like a Riemann sum because it is a Riemann sum. When we're rotating around the y-axis, our volume will be given by the sum from I equal 1 to n of 2 pi x f of x times dx. Here's the rule for the method of cylindrical shells. Let f of x be continuous and not negative. Define R as the region bounded above by the graph of f of x, below by the x-axis, on the left by the line x equal a, and on the right by the line x equal b. The volume of the solid of revolution formed by revolving the region around the y-axis is given by this definite integral. The volume from x equal a to x equal b of 2 pi x, remember that's the length of the stick of gum, times the function value, remember that's y, which represents the width of the gum, times the depth of the gum, or the height of the gum, which is the differential dx. Let's take a moment to look back at our original pictures coming from CalcPlot 3D. Let's go out to CalcPlot 3D now and let's see what this particular example looks like. When we're looking at CalcPlot 3D, remember to have the upper curve in as the top y of x, the bottom curve as the bottom one. CalcPlot 3D does not yet have the ability to do the disk washer method around the y-axis. Similarly, it does not have the ability to do the shell method about the x-axis. Instead, CalcPlot 3D uses the disk washer method about the x-axis and the shell method about the y-axis. Let's see how it works. We're going to set x squared to be our upper curve and the x-axis, x equals 0, to be the lower. Then we're going to go from x equals 0 to x equals 4. That's what we saw here in our particular problem. The region from x squared, the x-axis, the vertical line, x equals 4, revolved about the y-axis. Now let's take a look back at our CalcPlot 3D. Once we get out here, we can choose a representative rectangle. Notice, however, that my picture does not look right. I cannot see the whole thing. In other words, what I need to do is scroll up on the far left side and manipulate my axes so that I can see everything. Since we know we're going to x equals 4, and we know that 4 squared is 16, it makes sense that the y value should go up to at least 16. Since we're not dropping below the x-axis, we can leave the minimum value for y to be 0. Let's extend up to 20 on the y-axis. However, if I don't want to see a tick mark everywhere, I want to change the y to have tick marks every 5. I know that my x value should be going from 0 to 4, so I could instead, because I want to see on both sides of the axes, and I know it's rotating about the y, go from 0 to 4, but then I'll miss half my picture. Instead, I want to go from -5 to 5. Make sure you double the region on the opposite side of the axis of rotation so you can see the whole thing. You can either choose to let your x tick marks be 1s, or you can choose to let them go by 5s. To not clutter up the picture, I'm going to let mine go by 5s. What z value should I have? I really have no idea. I'm going to set some range and then see if I need to adjust it. I'm going to set this to go between, well, I have no idea. I think probably we'll start with -5 to 5 and just see if that works. If we can't see the whole thing, then we know we need to make the region larger. Notice that my focal point is not at the origin, but I don't want the focus at the origin. I know that my graph is going from 0 to 4 on x and from 0 to 16 on y. I do want to kind of look near the origin, so I think that what I'll do instead is I'll simply tell it to focus around y equal 8, but let the focus for x and z remain at 0. That would put the focal point there. Let's hit enter and see what we have. Now you can tell that while I have more of the picture, I still can't see it. Remember that you can put your mouse over the picture on the right and scroll in to see more of the picture. The problem is I can't see everything. What's wrong? Come over here and see what your Z-clip is. Your Z-clip is where it's taking cuts of the picture. I want to go further out. So what I'm going to do is change these and maybe go -10 to 10 and see if that gives me a better picture. Well, yep, that helped in that direction. Let's change the upper clip value to 10 and see if that helps as well. Notice that not changing the Z tick marks made a whole bunch of values. Let's change those to go by 5s as well. Now I can see the shape that's producing my solid of revolution. I can also see the one mark that I've got coming in the center. Notice that my Y max up here at 20 is probably more than I need. I could have stopped at maybe 16. That might give me a slightly better picture, but I can scroll in and lose the top part. It won't affect it too much. I can make the Format Axes menu disappear by clicking on its graph picture, or you can just scroll down. Now we want to look at the next region in here. My axis of revolution, notice, is the y-axis, which is the equation x equal to 0. If I rotate the region, watch what happens to the curve. As I rotate around, I'm getting more and more of the solid coming all the way around. Notice that it has an inner side and an outer side. That's given by the shape of the curve. If I take it all the way around, I can rotate the picture and see that the inside looks sort of like a vase, where the outside looks like a tube. Remember, to make your picture transparent, you can come down here and you can click on the gear symbol. The gear symbol will make it either less transparent, scrolling to the right, or more transparent by scrolling to the left. I'm going to make mine fairly transparent so I can see through it. Let's take a look now at a representative triangle. If I look at a representative triangle, what I'm actually trying to see there is the value of one of the strips being rotated. Let's show the representative triangle. If you unrotate it, it's easier to see. It's the red dot right here in the middle. That red strip is my rectangle. Now what I'm going to do is revolve the representative rectangle. This is the strip of gum that you're rotating. Let's turn it a little off kilter so we can see that as we rotate, it becomes a shell, not a solid disc, and not a washer. There it is. This is basically a cylindrical tube which forms my shell. You can also see the shape that's producing the graph with the inner value of x squared and the outer value being given by x equal 4. Now let's take and look at several shells. Click on the box that says Show in Washers or Shells. Right now it's set to 6 shells, which is a good number. Let's unrotate our representative rectangle so that we can see all of them. And let's rotate these rectangles. Let's rotate them around by revolving the washers or shells. Do you see what's happening on the inside? On the inside, you're getting basically this ring of shells coming around, stacked one inside the other inside the other. That's what I mean by using the stacking cups. This is what it looks like as you have them stacked one inside the other from above. If we rotate back out, you can sort of see the shape, but it's rather difficult because it's not quite transparent enough. Let's increase the number of shells. As we increase the number of shells, the shape begins to take on the shape that we're going to have eventually for the whole thing. If I rotate now so that I can look at the top, and it's taking a long time to rotate because there's lots of pictures in there, and it just has a hard time rotating with more than n equals 6, then I could see that on the inside, it does look, if I can get it just right, which I may not be able to do, it does look like I have a stick of gum inside a stick of gum inside a stick of gum, or a stacking cup and a stacking cup and a stacking cup and a stacking cup. This is the reverse of what I showed you a minute ago with the stacking cups. In this case, all of the shorter pieces are on the inside rather than the outside. You'll notice that up here it will give me the function value or the y value at any given point I choose by manipulating the slider bars. It also, by changing this value, will approximate the volume of the region using that number of shells, in this case 20. Yes, this will give you an approximation to do your homework, but I hope that it outweighs that disadvantage for me by helping you to understand what you're doing. Let's go back to our notes now and finish representing what we have in formula form. In formula form, what we're representing is the volume of that solid by integrating from x equal a to x equal b of multiple sticks of gums or stacking cups, one inside the other. We compute the volume of each stick of gum rotated into a circle by taking the circumference of the circle, 2 pi r, or 2 pi x, multiplied by the height of the stick of gum, f of x, or the y value on the function, which is, of course, the width of the gum, length times width times the thickness of the gum, which is the differential dx. Let's now look at example 1. In example 1, we want to find the volume of the solid created by revolving the region bounded by y equal negative x squared, y equals 0, x equals 0, and x equal 1 about the y-axis. The first thing to do is graph the region so you know what R looks like. The curve e to the negative x squared looks like this, between the lines x equals 0 and x equal 1. X equals 0 is the y-axis, x equal 1 is this vertical line. The line y equals 0 is the x-axis. Take these curves and now take each little rectangle and revolve it around the y-axis as a stick of gum. This will give you a whole lot of shells stacked one inside the other. Here's what we see here. Notice that the radius of each one is the x value on the curve, e to the negative x squared. That means the radius is just x. The height of each shell, or the width of the stick of gum, is the y value on each curve, which is e to the negative x squared. Recall that our formula is the integral from x equal a to x equal b of 2 pi r, where r is given by the x value, times the height, which is given by the y value on our particular curve, f of x, multiplied by the differential, which is dx. Let's set up our integral now. We have the integral from x equals 0 until x equal 1 given by the restrictions of our region. Our radius is x, so that the length of our strip becomes 2 pi x. The height of the strip is given by the height of the shell, which is given by the y value right there on the curve. The y value on the curve is the function value, which is e to the negative x squared. Once we have 2 pi x times e to the negative x squared, we need to multiply by the differential, which is dx. Go ahead and pause the video here, compute the calculus, and turn the video back on to compare your result to mine. In this particular case, recall that x is the radius and the function value is the height. This is really 2 pi rh times the differential. 2 pi RH gives us the area times the thickness, which gives us the volume of each shell. This can be calculated using a U-substitution to get pi minus pi divided by Euler's number E. Keep in mind that when the axis of rotation is not one of the coordinate axes, we'll have to adjust the radius. Let's take a look now at example 2 where this occurs. Find the volume of the solid created by revolving the region bounded by y equal x squared, y equals 0, x equals 0, x equal 1, about the line x equal negative 1. In this case, the volume of revolution is not one of the coordinate axes. Because it is not, we will have to adjust our radius. First things first, we need to graph the region R, which is completely contained and bounded by the curves y equal x squared, y equals 0, x equals 0, and x equal 1. Keep in mind that this region, if sketched quickly on the side, has to look like the region bounded by a parabola opening up with the vertex at the origin, which it will be if I make my ball big enough, the x-axis, which is y equal to 0, the y-axis, which is x equals 0, and the line x equal 1. In other words, the region we're talking about is this region right here that I'm now shading in with blue. This is the region that we're going to rotate about the line x equal negative 1. Over here on the left, you may want to draw the line x equal negative 1. To see what it's going to look like, draw the mirror image of this where the mirror is the dotted line. That means one on the other side is where I have the ball, and one on the other side of that is the straight edge. That would be a curved section like this, where I have something like this coming up on the other side. And then imagine drawing some strips that are circular in nature. This is what it would look like, something along those lines. I know it doesn't look very good when I hand draw it. I can't draw. So I recommend using CalcPlot 3D or some other online graphing system like GeoGebra 3D so you can see exactly what it looks like. Looking at our picture here, you can see that produced on CalcPlot 3D, we have y equal x squared, the x equals 0, which is the y-axis, x equal 1, which is a vertical line, y equals 0, which is the x-axis, and over here we have a dotted line of x equal negative 1. Let's put that information into CalcPlot 3D so we can see what it would look like. Recall the restrictions on our region. Y equal x squared, y equals 0, x equals 0, and x equal 1 about the line x equal negative 1. Let's pull up our CalcPlot 3D and put that in. X squared becomes the upper top of our region. The lower of our region is y of x equal to 0, in other words, the x-axis. On the left, we do want the vertical line, which corresponds to the y-axis, x equals 0. And on the right, we want x equal to 1. This needs to be changed from the 4 that we had in the previous example to 1. Our axis of revolution is not 0. This time it is the line negative 1. Go ahead and put enter so you can see the shape. You'll see down here that it is very small, which basically means this box is way too much. Keep in mind that since my curve is x squared and I'm only going out as far as x equal 1, my height isn't going to reach any higher than 1 either. Let's scroll up, click on the drop-down menu to format our axes, and we can let x go from, let's say, negative 2 to 2. That should be enough for that part of the curve. Then we can change our x tick marks from 5 to 1, or you could make them go to 2. and then it will only mark off -2, 0, and 2. The y marks, on the other hand, I only need to go from 0 to 1, so I think probably going by ones is plenty. In this case, I am going to go ahead and tell it to go from -1 up to 1 so I can see the whole thing in the center of the picture. In that case, because I've centered it already with the axes, I'm going to change my focal point to going back to looking at the origin 0, 0, 0. Or I may choose to use the focal point of -1, 0, 0, so that it's focused on the axis of rotation. That might be a better choice. Looking up here, then I can look at the z. It's not clear what z should be, and I don't expect you to be able to figure it out exactly in Calculus 2. Take a guess and set it to the larger of whichever x and y is, and that will probably be big enough. In this case, I've left it at -5 to 5, and that's probably okay, or you could change it to -2 to 2 if you prefer. Let's click in one of the boxes and then hit enter so we can see what it looks like. When I do that, it did give me a better picture, but notice it still looks small. This doesn't need to be fixed with the box, however. This can be fixed by scrolling on the picture. When I scroll on the picture, it will get larger. Notice that z going from -5 to 5 is overkill. If you want to change that, go ahead and change it. I'm going to try -2 to 2 and see if that produces a better picture. Now I've got a slightly better picture going on here. If you want the box to extend above your region, then you need the y value to go above 1. Say, -1 to 2. That ought to do it. Let's go ahead and change that now. Notice that I have x equal -1 as my axis of rotation and 0, 0 on the x or the y and z coordinates for my center of focus. Now what I want to know is, what does it look like? I'm going to close the format axes since I can see the graph pretty well. And what I want to know is, what do these strips look like? Looking at the strips, then, what I need to do is rotate it so that I can see the x and the y axis. To do that, you sort of more or less get the z to disappear by pointing straight at you. Y goes up and x to the right, and we'll see this shape here. Scrolling down, let's unrevolve the washers or shells so that we can see the original shape it came from. There it is right there. You'll see that I've already clicked on Show in Washers, and there are 20. This is giving us the shape of x squared between x equals 0 and x equals 1 and the x-axis. The representative rectangle is at 0.57, but you can change it to any spot you want. 0.5 is probably a pretty good place, though, since it's roughly right there in the middle. If we're looking at one of those and we want to revolve just the representative rectangle, this is what will show us what one single shell looks like. If you want to turn it sideways so you can see it a little better, you can rotate the picture a little bit towards you or a little bit away so that you can see the shell. It is a cylindrical shell, but it's a hollow tube. It's basically a piece of gum rotated into a circle. Now let's rotate all of the washers or shells. When we rotate all of the washers or shells, we end up with what looks like a bunch of stacking cups, one inside the other. However, notice that these stacking cups do not meet in the middle for the simple reason that our region does not touch the axis of rotation. The axis of rotation is the vertical line x equals -1, which did not touch our region over here under x squared above the y-axis from x equals 0 to x equals 1. That's why it's hollow on the inside. Let's go back to our sheet and see what the next step would be. we need to compute what 2 pi r h would become. We need the radius and the height, and the radius is given by the x value on the curve, and the height is given by the y value on the curve. However, in this case, it's not just x for the radius, because our axis of rotation is here at the line x equal -1. That means that from the y-axis, which is here in the middle, to the left is a length of 1, and from the y-axis to the strip is a length of x. That makes the radius going all the way from the strip to the axis of rotation 1 plus x, or x minus a -1. By looking at the picture and labeling the parts of the picture, you can find the radius relatively easily. Without the picture, however, it can be quite difficult. In this case, the height of the rectangle or thin strip does provide the value of the width of the piece of gum. It's this measure right here in the picture above. Now what we need to do is take 2 pi times the radius for the length of our strip of gum and the function value at that point as the height or width of the gum, and multiply by the differential, which is the thickness of the gum. That will give us the next piece. Let's write down our integral. Our integral is going to compute from, well, now hang on a minute, what does it go from? Let's look back at the picture. The first strip does not occur until x equals 0. The last strip occurs at x equals 1. There are no strips in the region between -1 and 0, so there's no integration happening there. I can't start until I have strips to integrate. So I start from x equals 0 and I go to x equals 1. Then I take the length of the stick of gum, 2 pi times the radius, which becomes 2 pi times x plus 1. Then I multiply that by the width of the stick of gum, which becomes the function value, which in our case is x squared. Then I multiply that by the differential dx. Be very careful that when the axis of rotation is not one of the axes, that you make sure to add or subtract any additional part to the radius, and that your limits of integration go from the first strip on the left to the last strip on the right, and not from the axis of rotation to the end of the region. Pause the video here, compute this definite integral, then turn the video back on to compare your answer to mine. This is a relatively simple integral to integrate. You should come up with 14 pi divided by 12. We have a relatively similar rule to this one for revolving about the x-axis. The difficulty, of course, will be that our differential will change from dx to dy, which means that our radius and the height of the strip will have to be written in terms of the variable y and not the variable x. The limits of integration will also be y values. Let's take a look at this second rule. This time, we approximate the flattened shell with a flat plate where the height is given by g of y and the width is given by 2 pi y. The thickness is still the differential dy. In other words, the height and the width have switched places. Or you could call it length and width. Or you can call it, well, you can call it whatever you like as long as you get the formula correct. Basically, the volume is given by 2 pi the radius, where the radius is given by the y value on the function, times the length of the strip or height of the strip, which is given by the function value at that point, times the thickness of the piece of gum, which is given by the differential. Adding up all of the stacking cups or all of the shells will give you a Riemann sum, and as you take the limit as the thickness of each piece of gum goes to 0 and the number of pieces of gum increase to infinity, this will give you the actual volume. Here is the volume. Let G of y be continuous and not negative. Define R as the region bounded on the right by the graph of G of y, on the left by the y-axis, on the bottom by the line y equals c, and on the top by the line y equal d. Then the volume of the solid of revolution formed by revolving the region R around the x-axis is given by the integral from y equals c to y equal d of 2 pi y times the function value at that point multiplied by the differential dy. In other words, strangely enough, with the shell method, to rotate around the x-axis, your differential is dy, and to rotate around the y-axis, the differential is dx. That's because with the shell method, the strips or thin rectangles are drawn parallel to the axis of rotation, so the differential is opposite. Let's take a look now at example 3. In example 3, find the volume of the solid created by revolving the region bounded by y equal x squared, y equals 0, and y equal 2 about the x-axis. This means that our function will have to be written in terms of x so that we can have y inside the equation. We'll have x equal some function of y. Our differential will also need to be dy. Let's take a look at setting it up. First, we have the equation y equal x squared, which looks like this. Our other restrictions are y equals 0, which of course is the x-axis, and y equal 2. When we look at y equals 0, we have this, and when we look up here, we have y equal 2. We really should have one more region added in here, which is, of course, that x is equal to 0. Let's add that restriction in now, since it really should have been in there in the beginning. Notice that we're only taking the region in quadrant 1 to rotate around the x-axis. Now, if we take this region, notice that our axis of rotation is x, which means it's horizontal. Since we're doing the shell method, we take the double L and we draw the strip parallel to the axis of rotation. That means that our thin rectangles will also run horizontally, just like the axis of rotation. The short end of the strip then becomes dy, and since it's dy, that means that this short end is the differential. The length of the strip, of course, is still going to be the height of our particular function. So we need 2 pi times the radius times the height. But remember that we're revolving this way. So if I were to draw the mirror image of this shape, it would look something like this, where we have the mirror image of it coming down here, and I've got another strip down here, and I'm rotating from one strip to the other strip, and there's my shell right there. Notice in this particular case that the radius is given by the value between the axis of rotation and the strip. There's no near end and far end. They're both equally distant from the axis of rotation. The radius is the distance from the axis of rotation to the strip. The height, of course, is given by the length of that strip. So we've got the formula integral from c to d of 2 pi y times g of y times the differential dy. Remember that this represents 2 pi r times h times the thickness, in our case, the thickness with respect to y. We need to know from what y value to what y value to make the limits of integration. Looking at the picture, where's the first box or thin strip? Right there at the bottom, right there where y equals 0. Where's the last one? Right up here at the top where we have the y value given by our restrictions of y equal 2. We're going from y equals 0 to y equal 2. That means that we can now draw or write down the integral for this example. The integral that we need to have is going to come from y equals 0, that's the c value, to y equal 2, that's the d value, 2 pi times the radius. Well, what is the radius? Well, what is a vertical distance? The vertical distance is y. This becomes 2 pi y times the height. What is the height? The height of the particular shell. The shell can be seen here, but you'd have to turn it sideways to really call it the height. That's the length of the strip. Well, how long is the strip? The strip is given by the x value on that curve. So the height here is given by the x value on y equal x squared. Well, how can I get that in terms of y? Notice that I can take the square root, and since I only have the right arm, it's the principal root. This is the equation y equal the square root of y. That means that the height, which is equal to x on that curve, is equal to the square root of y. This becomes the next part of the formula to fill in. Then we multiply by the differential, which is dy. This gives us the length of the stick of gum, the width of the stick of gum, and the thickness to give us the volume of the stick of gum. Go ahead and pause the video here and compute the calculus, then turn the video back on to compare your answer to mine. Again, this is a relatively simple integral to integrate. Now let's take a look at this particular one in the pictures to see what it looks like. Notice that we revolved around the x-axis and we have a relatively flat bottom on one side with sort of an arena-like seating on the other side. That's because when we had the original shape, we have this sort of shape here. So in a sense, it sort of comes in on the inside and back out. Unlike some of our previous pictures, this one's not hollow on the inside, since one image does touch its mirror image and they connect. However, it's infinitely thin at that point, right there in the center. Let's look at regions that are not in constant contact with the axis of revolution. We've already seen one of these. Let's look at another one. Sometimes we want to revolve regions about axes where the region is not constantly touching the axis of revolution. In the disk method, this resulted in the washer. For the shell method, it changes the radius from being one of the variables, either x if you're revolving around the y-axis, or y if you're revolving around the x-axis, to the difference between two values. We saw this in one of the previous examples when we rotated around the line x equal -1. In this problem, in example 4, we want to find the volume of the solid created by revolving the region bounded by y equal the square root of x minus 1, y equals 0, x equal 5, about the line y equal 3. The first thing to do, of course, is to graph the particular region so that you know where the bounded shape is. The square root of x minus 1 is a square root function that's been shifted to the right by 1. Y equals 0 is the x-axis. X equal 5 is a vertical line on the end. That gives us this purple shaded region here. In this particular problem, we're also going to rotate about the line y equal 3, which is shown up here. Since our axis of rotation is y equal 3, we should indicate that by drawing instead a circular arrow so that we can see what the axis of rotation is. Once you have the circular arrow indicating that y equal 3 is the axis of rotation, notice that the axis of rotation is horizontal. In the shell method, make sure that you draw them parallel. The strips or thin rectangles will be drawn parallel to the axis of rotation, which means the short end is going to be the differential dy. The height of the strip becomes the h in the formula, 2 pi rh. In this case, or in all cases, the radius goes from the axis of rotation to the strip at any point along the strip. It'll be the same everywhere. In our case, notice that this value right here is given by the y value, which is on the curve, square root of x minus 1. However, the radius is not that y value. The y value is measured from the x-axis up. So y, in this case, is coming from the x-axis up to that point. We want from here down. That's going to give us something different, which means 3 minus the y value on the square root. The y value on the square root is given by the square root of x minus 1, so our radius is 3 minus the square root of x minus 1. Notice that the height of the strip is also a difference. Again, our x value is measured from the y-axis, which is here. Coming out to the same point then, that is the representation of x. However, we have this vertical line at x equal 5. Since it is 5 coming all the way from the line at x equal 5 back to the x-axis, this measure right here, which represents the height, must be equal to the 5 minus the smaller distance of x. This gives us the height as 5 minus x, or 5 minus the square root function solved for x with the y values plugged in after solving for x. We do need to have things in terms of y because our differential is dy. That means that for the radius, we will use this version of the equation, and for the height, we'll need to use this version of the equation. If you're wondering how to compute the y squared plus 1, remember that the function value is given up here. To take that and solve for x, you need to solve by squaring both sides of the equation. Squaring both sides gives you y squared equal to x minus 1. Adding 1 to both sides tells you that x is equal to y squared plus 1. Since the height is 5 minus x, we can rewrite it as 5 minus the quantity y squared plus 1, which when we distribute the negative gives us 4 minus y squared. Now we're about ready to start putting it together, although we still need to know our limits of integration as well. To find the limits of integration, remember that we need to go from the bottom strip, since our differential is dy, to the top strip, which is here. Notice that the strips do not extend all the way to the axis of rotation, which is the line y equal 3. If you're not sure how to find the coordinates of this point, remember that it is the intersection between the line x equal 5 and the square root function, square root of x minus 1. We need to know when x is 5, what that y value would be right there. So we can write when x equals 5, y, which is equal to the square root of x minus 1, becomes the square root of 5 minus 1, which is the principal square root of 4, or 2. This means that our limits of integration go from y equals 0 on the x-axis to y equal 2. In a blown-up picture, you can see a little bit more clearly the relationship between the x value, the y value, the radius, and the height of the strip. We found that our integration limits are going to be y equals 0 for the bottom strip and y equal 2 for the top strip. Now what we want to do is set up our integral. We have the integral from y equals 0. Let me click off of that so it stops highlighting it, to y equal 2. We need 2 pi times the radius. Scroll back up to the picture so you can find that the radius is the value 3 minus y. Remember, everything has to be written in terms of y because the differential is dy. After 2 pi times the radius, the next thing we want is the height of the strip. This will give us the width of the piece of gum. Our height is given by 5 minus x. Now we can come down here and we can represent that by switching it to the form that we had in the previous picture. 5 minus the quantity, y squared plus 1, or 4 minus y squared. Finally, the last piece we need to add on is the differential, in this case, the differential dy. This represents the thickness of our shell, or the thickness of the piece of gum that we coiled into a tube. Pause the video here, compute the definite integral by evaluating the calculus, then turn the video back on and compare your answer to mine. In this particular case, we end up with the following. When you evaluate the integral, you should end up with 24 pi. You may want to go back and check. I think I may have mistakenly written 5 minus y on the integral, and it should have been 3 minus y, which is the radius value. Make sure that I didn't make that mistake. Now let's go on and look at what the pictures look like coming out of Calc Plot 3D. We've got our shape, and we're revolving about the line y equal to 3. When we revolve, you can see the shell, which looks like a stacking cup or a piece of gum coiled into a circle. When we put them all together, you can see that because we have this sort of curved edge on the left side, that we end up with an indentation or stacking behavior on that side. Whereas on the right side, because it is a vertical line, we get a flat edge. Because our region that we're revolving does not touch the axis of rotation, we do have a hole through the center. That's typical. Now let's take a look at regions bounded by two functions. In the disk washer method, when a region was between two functions and did not constantly touch the axis of revolution, we needed a washer. What happens in the shell method in a similar situation? In essence, we've already been doing these, where one of the functions was one of the axes. Again, it is the radius and height of the thin rectangle or strip that are affected by this change. Let's look at example 5. In example 5, we find the volume of the region bounded by the curve x to the fourth, y equal the sine of pi x divided by 2, rotated or revolved about the line x equal -1. First, graph the region. The region must touch all the bounding curves, in a sense, holding water. The axis of rotation is not considered a bounding curve. We want the volume of the region bounded by these two curves, x to the fourth and sine of pi x divided by 2. When you graph those two, you see that it's this region right here in quadrant 1. It could have also been the region over here in quadrant 2, But in our case, we didn't want it to be negative, so we only took the region from quadrant 1. You will need to make sure that you understand the correct region by either asking a question or asking for clarification or more carefully reading the description of the problem in WebWork. Hopefully, they're very precise. You can see my hand-drawn picture over here, which again is not terribly good, but it does kind of give the region. Now, when we blow this picture up a little bit, notice that over here we have the axis of rotation, which is x equal -1. The radius goes from the axis of rotation to the strip, wherever the strip may be. Notice that the distance from the y-axis, which is here in the center, is going to be from there to the axis of rotation is a distance of 1. The distance from the y-axis over to any strip is going to be the x value at the strip. That means that our radius must be the distance of 1 plus the x value of the strip, or x plus 1. Since we're rotating around the line x equal -1, which is a vertical line, our strips must run vertically. That means that our differential must be dx. If the differential is dx, we want x left in the equation, so we will leave the radius written as r equal x plus 1. Now we need to figure out what the height of our strips are. In this case, notice that the height is the y value on sine of pi x divided by 2 minus the y value on x to the 4th. That would be the difference between sine of pi x over 2 and x to the 4th. Since these are both written in terms of x, we can leave these as they are as well. The differential is given by the short end of the strip or thin rectangle, which is dx. Where are our rectangles? Let's draw the rectangles on now. The first rectangle occurs here at the origin. The last rectangle is here where those two curves intersect. I need to find the x value where the two curves intersect. To find the point of intersection, you could set the two equations equal to each other, the sine of pi x divided by 2 equal to x to the 4th. You can also just look at the picture, since it's pretty obvious that they're intersecting there at 1, 1. Let's think about that. When x is 1, the sine of pi over 2 becomes 1. 1 to the 4th is 1, and 1 equals 1. Therefore, these two curves do touch when x equals 1. When x equals 1, the value of the curve is also 1, since the sine of pi over 2 is 1. And that means that this point of intersection up here is the point 1, 1. Now we're ready to go ahead and set up our integral. Our h value is the difference between the sine function and the x to the 4th, and our r is x plus 1. We want to go from our first strip occurring at x equals 0 to our last strip at x equals 1, and then we take 2 pi times the radius, which was x plus 1, times the height, which in our case turned out to be a more complicated sine of pi x divided by 2 minus x to the 4th. This is 2 pi r here times the height here times the differential, which is dx. Take a moment here to pause the video and compute the calculus, then turn the video back on and compare your result to mine. First, note that you can factor out the 2 pi as a common factor. Then you can use the method of FOIL to multiply out the two binomial-like expressions. This gives us x times the sine of pi x over 2, with an x times negative x to the 4th giving us negative x to the 5th, 1 times sine of pi x over 2 giving us this term, and 1 times negative x to the 4th, giving us the last. Then we can go down and compute the integral of each individual term. Notice that this one has the variable x in 2 locations. Because we have x on the outside and x inside of a trig function, we'll need integration by parts. This one can be done using U-Substitution, and we don't need anything but the power rule for integrals to integrate the last 2. For the first term, however, we will need integration by parts. Notice that you use the mnemonic liate or L-I-A-T-E in order to compute which one becomes u. Since the algebraic part 2 pi x is coming before the trig part, we let 2 pi x be u. That makes du, or dv rather, sine of pi x over 2. Then you can do each of the steps in the integration by parts. Here I've illustrated the tabular method by taking the derivative of each expression on the u side and integrating each expression on the dv side. Then you take the product of the diagonal of each one with alternating signs. The last row has not yet been integrated, but because our last factor is 0, that last integral zeroes out and disappears. This second term, of course, can be done with the straightforward U-substitution you see here. When you compute the steps, remember to maintain the same limits of integration that were on the original integral. This gives us these steps that you see here. When plugging in the limits of integration, you will find that your final answer is 8 divided by pi plus 4 minus 11 pi divided by 15. This is a more complicated integral, but if you take your time and go slowly, I think you'll find that you can get the same solution I did. Let's now look at the last question in this particular section. Which method should you use? Should you use the disc washer method or should you use shells? Sometimes this is a matter of personal choice. Sometimes it is easier to do one as opposed to another. This depends largely on the region and the axis of rotation. The only thing you can do is to graph the region and consider the axes of rotation and what it might look like depending on which one you choose to do. Imagine in your head that you've got each of the formulas and try to visualize what pi r squared, the disc washer method, would be like compared to the shell method, 2 pi r h. Then make up your mind. On the exam, I will definitely let you know which one you're to use, or let you know that it's up to you and you can use the one that you prefer. This is the end of the video on the shell method for computing volumes of revolution.